Dielectrics. So we are going to start the fourth unit called dielectrics. Solids whose band gap is above 3 electron volt, we call it as insulators. So for an insulator, when an external electric field is applied, to an insulator whose energy gap is above 3 electron volt, electrons cannot cross the barrier. So this is the valency band and this is the conductional band. So the probability for jumping or moving an electron from the valency band to the conductional band is very, very low. So these type of materials are called as insulators. So these dielectrics are also called as insulators, but there is a probability of an electron moving from the valency band to the conductional band at very, very high temperature. So the dielectrics are the materials which have high specific resistance, a negative temperature coefficient of resistance, large insulation resistance. So these type of materials are called as dielectric materials. So these dielectric materials are insulators. So what they can transport electron from the valency band to the conductional band at very, very high temperature. So these materials have high specific resistance, negative temperature coefficient of resistance, and large insulation resistance. So this insulation resistance may vary depending upon the disturbances or the imperfections present inside the material. So these type of materials we call it as dielectrics. Dielectric polarization. So now let us consider a dielectric material which is placed in an external field. So now on the application of the external field, the field will act on the positive charge of the dielectric material and make the positive charges to move along the direction of the applied field, and the negative charge opposite to the direction of the applied electric field. So this is what is called dielectric polarization. Dielectric susceptibility. So dielectric susceptibility, the dielectric polarization vector P is directly proportional to the field intensity E. So otherwise this can be written as P is equal to epsilon naught chi of E into E, where chi of E is called as dielectric susceptibility, Dielectric constant, it is the ratio between the absolute permittivity and the permittivity of the free space. So the dielectric constant is represented by epsilon r. Epsilon r is equal to epsilon by epsilon naught. So it is the ratio between the absolute permittivity epsilon and the permittivity of free space epsilon naught. This is called as dielectric constant. Next is dielectrics can be classified into two different types. One is active, that is a dielectric material can be active and passive dielectrics. Dielectric materials can be broadly classified into two different types, such as active dielectrics and passive dielectrics. The dielectric material can be of any type. It may be a solid, it may be a liquid, or it may be a gas. For example, solid dielectric materials are mica, rubber, etc. These are all insulating materials or dielectric materials, solid dielectric materials. And we have some liquid dielectric materials such as oils and other materials. And we have some inert gases called gas dielectric materials. Even air is a dielectric material. So dielectric materials are broadly classified into two different types, that is active dielectrics and passive dielectrics. So in case of active dielectrics, when an external field is applied, from the name itself we can understand it actively accepts the electric charges. So it is called as active dielectrics. in case of passive dielectrics, these passive dielectrics are insulating materials. For example, in case of active dielectrics, we can have piezoelectric, ferroelectric, piezoelectric and ferroelectric materials are very good examples of active dielectrics. Whereas in case of passive dielectrics, it does not accepts the electrical charges, but it restricts the electrical charges, or otherwise called as insulators. So in a very good example of a passive dielectrics are, we can say, rubber, mica, everything. These are called as passive dielectric materials. Next is dielectric polarization. So dielectric polarization is broadly classified into 4 different types. One is electronic polarization, next is ionic polarization, orientation polarization, and last one is space charge polarization. So these are the 4 different types of polarization which takes place in a dielectric material: electronic polarization, ionic polarization, orientation polarization, and space charge polarization. So first let us consider the electronic polarization. Electronic polarization takes place between the positively charged nucleus and the negatively charged electrons. So for this, let us consider a monoatomic atom, and this is the positively charged nucleus, and this is the radius of the sphere, and this is negatively charged electrons. So before the application of the electric field, there will be no change. On the application of the electric field, on the application of the field, the positively charged nucleus will move along the direction of the applied field, and the negatively charged electrons will move opposite to the direction of the applied field. So on the application of the field, what happens? The position has been changed. The nucleus position has been changed. So let us denote this as X. This is the displacement on the application of the electric field. So due to the application of the electric field, 2 different types of forces acts. One is the Lorentz force, Lorentz attractive force, and Coulomb's repulsive force. On the application of the external field, 2 different types of forces takes place. One is the Lorentz force and the other one is the Coulomb's force. So this Lorentz force tends to separate the electron cloud and the nucleus, whereas this Coulomb's force tries to bring back to its equilibrium position. So at equilibrium, Lorentz force is equal to Coulomb's force. So the Lorentz force is equal to charge into field. So we know the charge of the electron is what? Electron is minus ZE and the applied field is E. Put this as equation number 2. Coulomb's force is equal to charge into total negative charges enclosed in the sphere of radius X. This is the sphere of radius X, and the total negative charges enclosed in the sphere of radius X divided by 4 pi epsilon naught into X square. So the total negative charges enclosed in the sphere is equal to charge density of the electrons into volume of the sphere. So we know what is the charge density. Charge density is what? Minus 3 by 4 ZE by pi r cube into 4 by 3 pi x cube. So that is the volume of the sphere. 4 by 3 pi r cube, that is the volume of the sphere. Since we have considered x, that is 4 by 3 pi x cube. So this, on simplifying, what happens? Minus 3 plus 3 gets cancelled. This 4 and this 4 get cancelled, and this pi get cancelled. So therefore minus ZE x cube divided by r cube. So substitute this in substitute equation 4 in equation 3. So put this as equation number 4, substituting equation 4 in equation 3. So on substituting equation 4 in equation 3, ZE divided by 4 pi epsilon naught x square into minus ZE x cube divided by r cube. So that is Z square, Z plus Z into Z square E square x divided by 4 pi epsilon naught r cube. Put this as equation number 5. At equilibrium position, equation 2 is equal to equation 5. That is minus Z E into E is equal to minus Z square E square X divided by 4 pi epsilon naught R cube. The applied electric field E is equal to Z E X divided by 4 pi epsilon naught R cube. So X is equal to 4 pi epsilon naught R cube E divided by Z of E. Therefore, the displacement of electron cloud X is proportional to the applied electric field E. So now two charges plus Z of E, that is the charge, that is the positively charged nucleus, and minus Z of E, negatively charged electrons, are displaced by a distance x to induce a dipole moment, and this dipole moment is given by induced dipole moment as mu of E is equal to magnitude of the charges into displacement. That is, magnitude of the charges is given as ZE into x. So now substitute the value of x from equation 6. So put this as equation 6, substitute the value of x from equation 6 in this equation. Therefore, mu of E is equal to Z E 4 pi epsilon naught R cube E divided by Z E. Therefore, mu of E is equal to 4 pi epsilon naught R cube E, or mu E is directly proportional to the applied electric field, or mu E is equal to alpha E into E. Alpha E is called as the electronic polarization, which is given by, which is equal to 4 pi epsilon naught R cube. So this is the electronic polarization, and it is given by alpha E. Next type of polarization which takes place in dielectrics is ionic polarization. This type of polarization takes place only in ionic crystals. It is the displacement of negatively charged cation and positively charged anion. So ionic polarization takes place only in ionic crystals. It is due to when an external electric field is applied to ionic crystals, the negatively charged cations and the positively charged anions are displaced, creating a dipole moment. This type of polarization is called as ionic polarization. So to explain the ionic polarization, let us consider an example. That is, let us consider an ionic crystal, NaCl. NaCl is an ionic crystal, Na and Cl, where Na is positive and Cl is negative. So on the application, before the application of the extra applied field, this is the position of the NaCl crystal. So on the application of the external field, this is the equilibrium position. Let us put it as x1, or positive, and this is negative. So this is the equilibrium position x1, x2. x1 is the displacement of the positively charged anion, and x2 is the displacement of negatively charged cation. Here the dipole moment mu I is equal to E into x1 plus x2. For the positive ion, the restoring force F is directly proportional to x1, or F is equal to beta 1 into x1. Put this as equation 2. And for the negative ion, the restoring force F is proportional to x2, or F is equal to beta 2 x2. Put this as equation number 3. Hence beta 1 and beta 2 are the restoring force constants, which depends on the masses and the frequency of the molecules in the ion. So this restoring force constants beta 1 and beta 2 are called the restoring force constants, which depends on the masses and the angular frequency of the molecules in the ion. So let us put small n as the mass of the positive ion and capital M as the mass of the negative ion, and omega naught is the angular frequency. So therefore the restoring force constant beta 1 is equal to m into omega naught square. Put this as equation number 4. And beta 2 is equal to capital M into omega naught square. Put this as equation 5. So now substitute the value from beta 1 in equation 2. So from F is equal to m omega naught square x1. So instead of beta 1, we are substituting the value of beta 1 from equation 4, m omega naught square. So therefore the restoring force F is equal to m omega naught square x1. Put this as equation 6, or F is equal to E into E. So therefore equating equation 6 and 7, we have E is equal to m omega naught square x1, or the displacement x1 of the positive ion is equal to E divided by m omega naught square. Similarly for the negative ion. Similarly for the negative ion, the value of x2 is equal to E divided by m. This is capital M omega naught square. Put this as equation number 9. Now adding equation, adding equation 8 and 9, we get x1 plus x2 is equal to E divided by omega naught square. It is common, so let us put it as 1 by m plus 1 by capital M. So we already know that mu I is equal to E into x1 plus x2, that is equal into E square E divided by omega naught square into 1 by m plus 1 by capital M. Or mu I is directly proportional to E, and alpha E is equal to where alpha, so therefore mu is equal to alpha I into E, where alpha I is equal to, alpha I is called the ionic polarization. Orientation polarization. This type of polarization occurs in dielectric materials where we have permanent dipole moment or with polar molecules. So these polar molecules have permanent dipole moment. So all these dipole moments are randomly oriented. Randomly oriented before the application of the electric field. So now on the application of the electric field, all these polar molecules align along the direction of the, that is the positive charges align along the direction of the applied electric field. So these type of polarization takes place only in polar molecules, and this type of polarization is called as orientation polarization. From the Langev's theory of paramagnetism, net intensity of magnetization is given as n mu square b divided by 3k bt. Since this principle can be applied for electric field also, so therefore the orientation polarization P naught is equal to n mu square e divided by 3k bt, where n is the number of atoms and P naught is equal to n alpha naught e, where alpha naught is the orientation polarization, therefore alpha naught is equal to mu square divided by 3k bt. This orientation polarization is inversely proportional to the temperature. Since T is in the denominator, it is inversely proportional to temperature. This is orientation polarization. This space charge polarization occurs due to the diffusion of ions and redisturb the orientation. This type of polarization is called as space charge polarization. So for example, so this is before the application of the applied electric field. So now on the application of the applied electric field, all the molecules will redistribute or reorient on the application of the applied electric field. Reorient on the application of the applied electric field. This type of polarization is called as space charge polarization. The space charge polarization is very minimum in all dielectric materials. Therefore the total polarization is the combination of electronic polarization plus ionic polarization plus orientation polarization plus space charge polarization. Since the space charge polarization is very minimum compared to that of electronic, ionic and orientation polarization, it can be neglected. So therefore the total polarization is 4 pi epsilon naught RQ plus E square divided by omega naught square into 1 by m plus 1 by m into mu square divided by 3k bt. So therefore the polarization vector P is equal to Ne into alpha. So that is the polarization vector P is equal to Ne into 4 pi epsilon naught RQ plus E square omega naught square divided by 1 by m plus 1 by capital M plus mu square divided by 3k bt. This is called as Langevin-Debye equation. This is called as Langevin-Debye equation. So in the examination they may ask you a question, that is explain the different types of polarization in dielectrics, or they may ask you derive Langevin-Debye equation. So if they ask you to derive the Langevin-Debye equation, you have to explain all the 4 different types of polarization and the total polarization. You have to explain the total you have to derive the total polarization, and this final equation P is equal to Ne into 4 pi epsilon naught RQ plus E squared by omega naught square into 1 by m plus 1 by capital M into mu square divided by 3k bt. You have to derive this equation, and this equation is called as Langevin-Debye equation.